Hello everyone, welcome to COLING 2022. I'm Ziwei Yang from Jilin University. I'm presenting our work, a Coarse-to-fine Cascaded Evidence-Distillation neural network for explainable fake news detection. The authors of this work include Jin Ma, He Chang, Hong Zhang, Ziyang, and Yichang. In this work, I would like to introduce our work as the following 4 parts. First of all, for introduction. Recently, the explosive growth in fake news has increased the demand for fake news detection and intervention. For example, the widespread fake news about the end of war in 2012 has caused great confusion and panic. 2016 United States president election demonstrated that political misinformation has potential to change election outcomes. COVID-19 rumors about COVID-19 was then made a lab in Wuhan, China, which is a malicious slander against China. After the war broke out of Russian-Ukraine war, it was reported that Ukraine Zelensky had fled the capital Kyiv and its center. Such massive fake news has caused great confusion, panic, and heavy casualties, requiring effective methods to automatically check their veracity and provide explanations. In this work, the workflows of our proposed method and existing baselines are totally different. Existing fake news detection methods aim to classify pieces of news as true or false and provide veracity explanations, achieving remarkable performances. However, they often tailor automatic solutions on manual fact-check reports, suffering from limited news coverage and debunking delays. In contrast, we present the first study on explainable fake news detection directly utilizing the wisdom of crowds, alleviating the dependence on fact-check reports. For example, during the COVID-19 pandemic, there is a claim saying microwaving fabric masks is a good way to sanitize them for reuse, as shown in Figure 1. We could see that certain amounts of relevant raw reports, for example R1, R2, and Rn, were disseminated on various media outlets. And the fact-checker were able to judge its veracity and write a debunking report for explanation. Thus, we can conclude that, first, some reports contain underlying evidence for verifying this claim. Second, not all sentences in the check-worthy reports, for example R1 and Rn, are helpful for final inference. Third, human explanations for verdicts can be composed of evidence in raw reports. Therefore, to use the wisdom of crowds, we assume that crowds of relevant raw reports contain evidence for detecting fake news and explaining verdicts. Second, for our proposed method, as shown in Figure 2, to mitigate the dependence on fact-check reports, we propose a general coarse-to-fine cascaded evidence-distillation neural network to detect fake news and explain verdicts directly using raw reports. It consists of 4 parts: hierarchical encoding, report selection, explainable sentence extraction, and veracity prediction. As we know, Words can form a sentence, and sentence can form a document. Thus, we introduce a hierarchical encoding in our work. Specifically, given a claim or a report sentence T equals to W1 to WT. First, for word embedding, WT is a d-dimensional vector initialized using pre-trained language model, for example, BERT. Second, for sentence encoding, we use the spatial token CLS embedding from the final contextual layer of pre-trained language model as the sentence representation. Third, for document encoding, the document encoder consists of a bilostome and a max-pooling layer as follows, where h-type ij denotes the j's sentence in the i's document. We use max-pooling on all sentence representations for the i's document representation hi. On top of hierarchical encoding, a coarse-grain report selection module is introduced. In this module, a global attention is utilized to obtain the significance score for each report as follows. We use all scores to rank all reports and select the top K results as the CofCED reports. The coarse-grain report selection aims to distill the CofCED reports from massive raw ones by ranking, which automatically narrows down the coverage for evidence-distillation. Furthermore, a fine-grained, explainable sentence extraction module is introduced. In this task, 4 semantic features are integrated to predict the probability of each sentence. As shown in the equation, the first part is claim relevance, which measures the topic coverage of each sentence regarding the claim. The second part is richness, which measures the content informativeness of each sentence containing evidence. The third part is silence, which measures the significance of each sentence regarding the entire report. The last part is non-redundancy, which measures the novelty of each sentence regarding previously selected explainable sentences. Besides, a softer threshold is designed to extract the explainable sentences S1 to SE. For final veracity prediction, we aggregated the recognitions from the obtained evidence and reports for a target claim respectively as follows. H plus is fed into a multilayer perception to predict the veracity level as follows. Finally, for model training, we adopt supervised learning and jointly optimize the above 3 subtasks in an end-to-end model. Third, for experiments, fact-check reports are not always available for breaking news and are mixed up with massive raw reports, which may contain more semantically irrelevant and redundant information. Thus, we collected 2 new datasets, that is raw fact and liar raw, considering a more general situation of detecting and explaining fake news with relevant raw reports. The statistics are shown above. We conducted experiments on both datasets to evaluate the veracity prediction and explain generation performance of our methods. For veracity prediction, given claims and raw reports, our CofCED achieved much better performance than other baseline methods as shown in Table 2, demonstrating the effectiveness of CofCED for explainable fake news detection utilizing the wisdom of crowds in terms of precision, record, and McAfee score. Besides, for ablation study, our method significantly outperforms its ablation counterparts on both datasets, demonstrating all components contributed to detecting fake news. For explanation evaluation, overall, our methods achieves the best performance on raw fact and comparable raw scores with GEM-FEMT on their raw, suggesting that CofCED can effectively distill explanations that also contributes to the final veracity prediction. For case study, we found that the selected sentences with high probabilities can better justify the prediction. For example, we found claim and don't have a tweet account as shown in Table 5. In addition to being a state-of-the-art method for explainable fake news detection, our CofCED has the additional advantage of being very explainable for sentence extraction. For parameter sensitivity study, Figure 3 shows the results of CofCED under different values of the trade-off parameter. The colored dashed horizontal lines denote the performance of CofCED with our multitask adaptive weighting. See Appendix B. These two figures shows that CofCED with multitask adaptive weighting is more effective and robust. Besides, Figure 4 also shows the CofCED under different values of maximum number k for report selection. To balance performance and resource, k is set to 12 and 18 for raw fact and liar raw respectively. Finally, for conclusion, our contributions are as follows. To the best of our knowledge, we present the first study on explainable fake news detection directly using the wisdom of crowds, alleviating the dependency on fact-check reports. Second, our model has the advantage of revealing insight into the generation of veracity explanations from various perspectives. Finally, we construct two realistic datasets, raw fact and liar raw, consisting of raw reports for each claim. Experimental results on benchmarks demonstrate the effectiveness of CofCED for detecting fake news and explaining verdicts based on raw reports. Thank you for your listening.